Hello viewers, good evening. Dr. T. N. Oza here. Today I am going to present to you a very small video. In this video, we shall discuss some questions and see how the spectral data can be used to arrive at the structure of the molecule. This video, very small, will be very helpful for beginners. First question, how can you determine the structure of the compound of molecular formula C3H6O, whose infrared spectrum clearly shows a strong absorption band at about 1725 per centimeter. If this much information is given, we have to determine the structure of the compound. How do we proceed? A strong infrared absorption band near 1700 to 1900 per centimeter is a sure shot indication of the presence of C double bond O in the molecule. This band corresponds to the vibrational frequency of the C double bond O molecule. Saturated open chain carbonyl compounds and ring carbonyl compounds having rings 6-membered or larger. So the C double bond O stretch band between 1720 to 1735 per centimeter. Therefore, we can say with surety that the given compound is either a ketone or an aldehyde. Possible structures are acetone or propionaldehyde. So let us proceed further. We have to decide between these two structures. Both NMR and IR spectral data can be used to decide the correct structure. For acetone, there will be one NMR peak at about 2.1 ppm. For propionaldehyde, there will be 3 peaks. A triplet for methyl, a multiplet for methylene, and 1:2:1 triplet for aldehydic proton. And very characteristic, the aldehydic proton absorbs downfield between delta 10.5 to 9.5 ppm. In the carbon-13 spectrum, acetone will see 2 peaks. Propionaldehyde will exhibit 3 peaks, one for CH3, one for CH2, one for CHO carbon. So on the basis of NMR, we can distinguish between these two. Also, the aldehydic CH absorption appears as a weak band between 2820 to 2780 reciprocal centimeter. This peak will not be shown by acetone, but it will be shown by propionaldehyde. So we can say how the infrared and NMR data can be wisely interpreted to arrive at the correct structure. Question number 2. Both dimethylacetylene or 2-butyne and 2,2,3,3 tetramethyl-butane, we have both show single NMR absorption. So we have to see how can we distinguish between these compounds based on spectroscopic data. Let us proceed. Dimethylacetylene will show one H1 NMR peak at about delta 1.5 ppm. Also, the other compound will show only one peak, but the delta value will be around 0.9 ppm. Clear-cut difference between the two. In IR, neither of these two compounds will show any absorption about 3000 reciprocal centimeter, but the mass spectrum of dimethylacetylene will show parent ion peak at about M/Z54. For the other compound, which is highly branched, definitely the parent ion peak will be absent. So again, we can see how IR, NMR, and mass spectral data can be used to arrive at the structure. Third question reads like this. The electronic spectrum of acetone shows 2 bands, 280 nanometer, epsilon 15, and 190 nanometer, epsilon 1000. We have to assign these bands to the type of electronic transition, and we need to explain why one peak is so much weak. So let us go ahead. The 280 nanometer band, which is very, very weak, corresponds to N to pi star symmetry forbidden transition. The other peak at 190 nanometer, having a bit higher absorptivity, corresponds to symmetry allowed pi to pi star transition, and it is weak. So symmetry forbidden bands are very weak. Symmetry allowed bands are strong, intense. Here a basic question arises: why symmetry forbidden bands are allowed at all? The reason is the molecules are continuously vibrating, and due to vibration, the strict symmetry rules are broken down to some extent. That is why weak bands appear. Question 4 reads like this. The gamma ray irradiation of ammonium perchlorate crystal was studied in C2. That is inside the sample cavity of ESR spectrometer. The 12-line ESR signal was recorded. We have to explain this observation, mainly the switching pattern. So let us go ahead. Ammonium perchlorate upon irradiation, high energy radiations, gets decomposed into two molecules, and further irradiation ionizes ammonia molecule, giving ammonia cation radical, which is ESR responsive because it contains unpaired electron. The ESR signal has the multiplicity M given by the formula 2N1I1 plus 1 multiplied by 2N2I2 plus 1. Here, N1 is the number of nitrogen nuclei, which is 1, having spin quantum number I1, which is 1. N2 is the number of hydrogen nuclei, which is 3, having spin quantum number half. So when we put these values into the above equation, we get M equal to 12. So the multiplicity of 12 has been explained simply. Other question, which is somewhat related to the previous question, is look at the ESR spectrum of transient NH radical species. The same formula which we used for the earlier question, 2N1I1 plus 1 multiplied by 2N2I2 plus 1. When we put the values, N1 equal to 1, N2 equal to 1, I1 equal to 1, I2 equal to half, we get the result 6. This is the theoretical explanation. In reality, the number of lines may be lesser due to overlapping. So by reading these 4 questions, the beginner students can learn the preliminary method of how to use spectral data to arrive at the structure of the molecule. This video will be helpful, so I believe. Thank you very much.